be in your pair deck tab, but it really doesn't matter at this point exactly. So you do want to have the pair deck open. And so today's lesson, solving linear systems by graphing. This is lesson 11.1 out of your text. And how can you find the solution of a system of linear equations by graphing? We have some learning goals for today. There's 3 of them. I can determine if an ordered pair is a solution to a system of linear equations. I can use a graph to determine if a system of linear equations has no solution, one solution, or infinitely many solutions. Anytime you try to solve a system of linear equations, one of those 3 things will happen. You're either going to have no solution, one solution, or infinitely many solutions. And the last I can statement, I can graph a system of linear equations to determine the solution. All right, so some vocabulary so we know what we're talking about. When we talk about a system of linear equations, sometimes that's just referred to as a linear system, or I might just even say system, okay? But I'm talking about a system of linear equations. This we have 2 or more linear equations with the same variables. The ones that we're going to be looking at have 2 variables and just 2 equations, right? And typically the 2 variables that we have are x and y. A solution of a system of linear equations is an ordered pair that satisfies all the equations in the system. So our solution, if we have one solution, it'd be an ordered pair, an x, comma, y ordered pair. Or it could be infinitely many ordered pairs that satisfy a system. So the word coincide, we'll talk about that. If we say 2 lines coincide, that means they correspond exactly. They are identical. And you saw that in the video. They showed infinitely many solutions where they graphed one line and then they graphed the second line and it was directly on top of the first one. That would be an example of infinitely many solutions, because when you're talking about solutions of a system, we're trying to see where do those 2 graphs intersect. And if they're the same line, they intersect everywhere that they're graphed. So that's why it's infinitely many. And then parallel lines, hopefully you remember, lines in the same plane that do not intersect, okay? And so if 2 lines are parallel and we graph 2 equations from a system and it turns out that they're parallel and we're looking for where they intersect to find the solution, if they never cross, they never have a point of intersection. So there's no solution in that case. So we're always going to have one of those 3 things. There'll be one point of intersection, they'll intersect everywhere, or they'll intersect nowhere. So you either have one solution, no solution, or infinitely many. So this is an example here. What does it mean for an ordered pair to be a solution to a system? So we have the system of equations, x plus 2y equals 6. And x minus y equals 3. That is our system of linear equations. There's 2 of them, and they have the same variable. Okay, so that's our system. And the solution, it says, is the ordered pair 4, 1. So we can visually see that over here in the picture. If I graph these 2 lines in the coordinate plane, they intersect at the ordered pair 4, 1. This is the only point that they cross at. So this is the only solution. There's one solution, which is one ordered pair. Sometimes when you're graphing to solve, it's not always incredibly accurate. So you can check your work with what we are showing here. This is using algebra to show that this ordered pair actually does satisfy both equations. So if we take equation 1, which is x plus 2y equals 6, the first one, and then I replace the x with 4 because the x coordinate is 4, and replace the y with 1 because the y coordinate is 1, and then evaluate it to see that actually I end up with something that's true. 6 equals 6 is true, so it does satisfy the equation. And then I would show that with the other equation. Equation 2, x minus y equals 3. Again, replacing the x with 4 because 4 is the x coordinate, and replacing the y with 1 because 1 is the y coordinate, and then evaluating it to see if we get something true or false. 3 equals 3 is true, so it works. So since the ordered pair is makes both equations true, it is the solution. So we're proving that it's true. If you were given an ordered pair and you plug it in and you get something that's nonsense, like 2 equals 1 or 10 equals 12, that would be a case where it is not a solution. Okay, this is the only pair of numbers, x as 4 and y as 1, that makes both equations true. So I'm going to let you try one of these. And so it says, is -2, 2 the solution to this system of ordered pairs? So the graphing method is one way to put it in here and see where they intersect to get this. If I get -2, 2, then that shows that this is the solution to this ordered pair, to this system of equations. If I do the algebraic way here, I can prove it like I did on the last slide, okay? So last slide, we plugged in the values to see if we got 2 true equations or not. So here, I've already written it out for you. So y equals -2, x minus 2 is here. That's the first equation. Second equation, x plus 2y equals 2 is here. All right, so what you're going to do is you're going to replace the y with the y value. Replace the x with the x value and see, do you get a true or a false equation? Then you're going to come over here, replace the x with the x value of -2, and replace the y with the y value of +2, and see, do you get a true or a false equation? If you get 2 true equations, then it is the solution. If one of these is false or both are false, then it is not the solution. They have to both give you true statements at the end, something like 5 equals 5, 6 equals 6. If you get something that's nonsense, like 1 equals 2, then it fails. All right, so that's what you're going to try to do right now. I'm going to give you about 5 minutes to do that. And find you a timer. What we did here, and if I show some of your responses, this person deleted theirs. This person put some points in the coordinate plane. Yes, it is an ordered pair. Yes, it is an ordered pair, but we want to know, is it the solution? This person looks like they circled one side, and now they're writing yes. Okay, here's someone who did what we were supposed to and show the work. All right, so good job to this person here. We can see replacing the y with 2 and the x with -2. Simplifying this, we end up with a true statement, 2 equals 2. So this side's true. Then we check over here, plugging in the values, and we get another true statement. Okay, so since they're both true, yes, it is a solution. This person put yes, and they graphed a line. They said it is a solution, so they plugged it in and probably did the rest in their head. This person wrote 2 equals 2 and 2 equals 2. So on this next slide here, just to show you, I did find an example where they did it correctly, where they showed this work 2 equals 2 and 2 equals 2. Now, if you were to graph these lines, this is what they look like, and you can then see that they do intersect at one point, and that point is the coordinates of -2, +2. Okay, they're right there. That's the only place that they cross. It's the only place they intersect. So that is the only solution to that system. This is a concept map to kind of help you understand. So in the middle, it says we have solution for a linear system of equations. When we're talking about solutions, the definition is that the solution to a linear system satisfies, yeah, okay. I thought maybe I was on mute, but I'm not. I'm good. Okay. The solution to a linear system satisfies both equations in the system. And that's what we were doing on this last slide here. We're showing this algebraic work here in pink, where we're working it out. This is showing it satisfies both equations in the system. And then an example of that is, here's a system of linear equations. There's two equations, both with x and y. And the picture shows that they intersect in one point, and that point is -2, 0. Okay, so that's an example of a system with one solution. And then over here, we have some facts. Well, actually, before I look at facts, let's look at the non-example. Okay, so we saw the example where there's one solution. A non-example, we have a different system, two equations with x and y as the variables. And there is no solution, because if you look at the graph, these two lines are parallel. They will never intersect, so they never have a solution. There is no solution. Up here, the facts now. So the solution is an ordered pair if the two lines intersect at one point, and that's what we've seen here in the example. There are an infinite number of solutions. Okay, in the case where the two lines coincide, they turn out to be the same exact equation. So if your system consists of two equations that are the same equation, then there are an infinite number of solutions is what we would write. And finally, there are no solutions, okay, if the two lines have the same slope and have no points in common. So that's what we saw in the non-example. This is an example where there's no solution. Okay, now whenever you graph a system of linear equations, you graph two lines in the coordinate plane, one of these three things will happen. Okay, one of these three things has to happen. They're either going to intersect in one point and there's one solution. They will turn out to be the same line. They will intersect everywhere and there'll be an infinite number of solutions. Or they will be parallel lines. They'll never intersect and you'll never have a solution. So the number of solutions is 0. You either have 0, an infinite number, or 1. This next slide here, I'm going to have you go to your Pear Deck tab and draw in the purple boxes. You're either going to draw a 0, a 1, or an infinity. Because 0, 1, or infinity. Okay, so find the parallel lines, and that means there's no solutions. Find the intersecting lines, and there's one solution. Find where it's the same line, and you write there's an infinite amount, or you can write the infinity symbol. Okay, so there's 3 examples of 3 systems that are graphed. Tell me, how many solutions does each picture have? Okay, I don't think we need quite 3 minutes or 5 minutes for this, maybe 2 minutes. Is up. Please tab back to our Google Meet tab, and I'm going to share some of your responses and see how we did on this one. So you had to identify the number of solutions shown in each graphed picture. Let's see. That one is incorrect. That one is incorrect. Nope. 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 So guys, when you're trying to figure out how many solutions there are, you're looking for the number of places that the lines intersect. A solution to a system is represented by where the lines intersect. Where do the lines cross? So this person got it right. Starting over on the right-hand side, there is one solution shown here because the 2 pink lines only meet one time. They only cross once. In the middle, these lines are parallel. They're always the same distance apart. They never cross. So there's never a solution. So there's 0 solutions. And then the last one it looks like there's just one line here, except it's labeled as both equations because these are the exact same equation, just written differently. And so they overlap. They coincide is the mathematical vocabulary term. They coincide. So if you try to figure out how many times they intersect everywhere along this pink line, the entire line. So there's an infinite amount of solutions. Okay, there's an infinite amount of ordered pairs along this line, which each represent a solution. There are no ordered pairs to represent a solution. There is one ordered pair right here. The ordered pair is actually -2, +4. That's the solution that you see in this picture all the way to the right. Infinity, 0, 1. Great. Infinity, 0, 1. Awesome. Too many for numbers. So that's when we use the infinity symbol, because there are too many to even express it. Yes. Okay. Let's move on. Slide 9. And so this is the last I can statement is you need to be able to solve a system by graphing. So if you're just given a system of linear equations, that's what you have here. 4x plus 2y equals 4, -6x plus 3y equals -18. It's not saying, hey, is this ordered pair the solution? It's saying find the solution. Okay, and so in that case, what you want to do, if we're trying to do that by graphing, is we want to graph those equations. These are right now in what we call standard form. Remember, the x term, the y term, the constant term on the other side of the equal sign. This is called, these are both in standard form, which are, there's different ways to graph lines. If they're in standard form, you might want to find the x and y intercept and then plot those 2 points and connect a line that way. In this example, what we're doing is rewriting each equation into slope-intercept form. Okay, remember that's y equals mx plus b. So if I rewrite 4x plus 2y equals 4 in slope-intercept form, I have to move the x term to this side, and then I have to divide everything by 2, and I end up with y equals -2x plus 2. To rewrite -6x plus 3y equals -18 in slope-intercept form, I have to get this x term out of here. So I add 6x to both sides, and then I divide every term by 3, and I end up with y equals 2x minus 6. Once you have them in slope-intercept form, you're going to then graph the lines. Okay, so we graph them. You use your y-intercept first, +2, which means I start here, and then I use the slope of -2. So you can go down 2 and over 1, down 2 to the right 1, down 2 to the right 1. And then I can graph y equals 2x minus 6. So you start at -6, which is down here. And use your slope of +2 to rise 2 units, run 1 unit, rise 2 units, run 1 unit to the right. You keep doing that until you have your 2 lines graphed. And then you look. Do those lines intersect? They do. They intersect in 1 point exactly. They intersect at the point 2, -2. X coordinate, y coordinate. 2 lines up with 2 on the x-axis. -2 lines up with -2 on the y-axis. So the solution to the system is 2, -2. You're going to try this. I am going to put on student paste mode. All right. So time-wise, 5 minutes for you to try this one. Okay, just try 10 and then we'll go over it. Okay, so you have 5 minutes. You're going to toggle back to your Pear Deck tab. Show you how to solve this system by graphing, and then it'll be your homework to do the last slide. So what we want to do first is rewrite both equations into slope-intercept form. And so x plus y equals -1. That means currently the x is on the wrong side, so I need to move it to the other side. Y equals negative x, and it's -1. So when you move something to the other side, it changes its sign. And then for the second equation, we have negative 2y equals, and we're going to move that 4x term to the other side of the equal sign, so it becomes negative 4x and -16. Okay, and then I just need to adjust this so you can see the whole thing. And well, I'm almost done rewriting this in slope-intercept form. I'm going to have to do another step here. Enter. I have to divide everything by -2. So that's going to change it to y equals -4 divided by -2 is going to be positive 2x, and -16 divided by -2 is positive 8. All right, so now that I have two equations in slope-intercept form, and even though this one kind of doesn't look like it's in slope-intercept form, we can write it a little bit differently. So instead of just negative x, I can make it negative 1x, okay? And I can think of it as plus -1. I'll just adjust this because you can't see it like that. Oops. And so once you have your two equations written in slope-intercept form, then it's easy to graph them because now you can identify what the slope is and what the y-intercept is. So here, our slope is going to be -1, and I just put that over 1, so I have a rise over run. And then our y-intercept is -1. That tells me where to begin. Those are my m and my b. And then for this one, our slope is positive 2, and I think that's a fraction is over 1. And our y-intercept is 8. Okay, so now I'm going to be able to graph these two lines, graph both equations, and then I'll be able to determine the solution. And so I realize I'm now going into our next class. So if you have to leave, I understand this will be in the video, but if you want to just hang on, I'll be done in a minute and you'll be able to see how this turns out. So I'm going to use the pencil tool and I'm going to plot some points. So first point I'm going to plot is the y-intercept, which is -1, which will be right here. And then I'm going to use the slope to rise up 1 and over 1 in the negative direction. And I can repeat that as many times as I need to. Okay, and you can also reverse it in the other direction. If I draw a line through these points, I get this equation. And you should always have arrows at the end of the line that you graph. And then we're going to graph the other line. So my y-intercept is positive 8. So on the y-axis, I go to positive 8, make a point, and then I'm going to use my slope of positive 2 over 1 to rise 2 units and run 1 in the positive direction. And I'm off the grid. So I need to reverse that pattern. I need to go down 2 and to the left 1, down 2 to the left 1, and repeat. And you can see there is my point of intersection. I can now draw the line. Through these points. Put my arrows at the ends. And I can see that my solution it lets me type. Okay, my solution is the ordered pair. Well, my x coordinate is -3, and my y coordinate is positive 2. Okay, and it's always a good idea when you solve a system by graphing to check your work, which means see if this makes sense and satisfies both equations. So for the top one, if I replace the x with -3, and then I add 2 to it, I get -1, which is exactly what I would have gotten if it was true. And it is true, so that's great. And then for the next equation, it's 4 times my x coordinate is -3. And to that, I'm going to subtract 2 times my y coordinate, which is 2. And, you know, does that equal -16 is the question. Well, 4 times -3 is -12. And then minus 2 times 2 is 4. And so does that then equal -16? Yeah, it does. Okay. -12 minus 4 is -16. So it checks out. And so you can do like this is just to show that you checked your work. And they work out for both of them. So that is your solution, -3, 2. Okay, I'm sorry I went over. If you're still hanging out, thank you.